Hello, welcome to our next video. This is going to be covering what integration is really all about. And this is going to be quite an advanced video. And this is going to be an overview of integration theory via enriched categories and homological algebra. We're going to be starting off by looking at Gaussian integration, and then we're going to move into ends, coends, the Beck-Chevalier condition, the Stokes-Cartan theorem, as well as their relation to homology and cohomology. Let's begin. We're going to start off with a highly abstract overview in terms of the Gaussian integral, which is going to be our base example for the beginning of this video. That is that the integral I is equal to the definite integral from negative infinity to infinity of e to the negative x squared dx. Traditionally, we begin computing this by squaring it. So I squared is equal to the integral over the reals of e to the negative x squared dx times the integral over the reals of e to the negative y squared dy. We can combine this together into a double integral over the two-dimensional Euclidean vector space of the function e to the negative x squared plus y squared dx dy. Next, we will convert to polar coordinates as is traditional procedure. So I squared becomes the integral from 0 to 2 pi times the integral from 0 to infinity of e to the negative r squared r dr d theta, where r dr d theta is the factor we get for our Jacobian. As we should be familiar with by now, I squared computes to pi, such that I is equal to the square root of pi. So therefore, the integral from negative infinity to infinity of e to the negative x squared dx is the square root of pi. Now let's consider this from a much more abstract perspective to see what's really going on. Integrals are projections from a relatively incoherent global space, let's call it Cn+1, to a relatively coherent local space, let's call it Cn. And in terms of the Gaussian integral, this appears as the following form, where we have a map phi from c to the n+1 to Cn that acts as the opposite of derivation, where mu is a measure. So the integral over phi of e to the negative x squared through the measure on x. And as the integral itself acts as a projection from incoherence to coherence, the exponential then defines the local decay of incoherence as we approach a coherent structure under projection. And the map phi then can be seen as acting as a boundary for our integration theory, and in this case, that boundary theory is the real number line itself. This means that the output of the projection itself lives in the boundary of the nth coherence class. And the target boundary theory is therefore written as the following. The boundary of the nth coherence class is isomorphic to the real numbers. And the set of real numbers must be the terminal coherent boundary theory for our one-dimensional continuous measurement. This implies that our act of integration is a measure of coherence attained by resolving an incoherent ambient space along a real axis into a locally coherent object, which in this case, a locally coherent object within the real numbers is just a scalar. But when we squared the integral, we didn't really just multiply two numbers. What we really did is form a tensor product of projections on an ambient space. So the integral over phi of e to the negative x squared through the measure on x tensored with the integral over phi of e to the negative y squared through the measure on y. And this is the act of integrating over a biclass Cn cross Cn of coherent structures. Shifting to polar coordinates is then seen as the act of identifying a coherent radius as an invariant under rotations. And this is a symmetry reduction of an ambient space by the orthogonal group of dimension 2, O2. And that's analogous to gauge fixing. So the product integral over the two-dimensional Euclidean vector space projects through a quotient by the two-dimensional orthogonal group, and the Jacobian, which is r dr d theta, is a measure of density on that quotient. The Gaussian integral can be interpreted as normalizing the transition from potential to the actual, or in terms of energy, from potential to kinetic, and thus its square represents the coherent volume obtained when we regularize against incoherence. So let this symbol gamma represent the unit disk. Then the projection from our ambient space to a local object gives the square root of that coherent volume when fully regularized. Therefore, I is equal to the volume in the nth coherence class of gamma to the power of 1/2, which is to say, essentially, we have the square root of the volume of gamma. The fundamental constant that preserves coherence under rotation in the minimal dimension where rotational invariance can occur is the constant pi. And so its square root is the normalization constant that ensures that projections remain invariant under orthogonal transformations within a coherent frame. So our volume within the nth coherence class of gamma to the power of 1/2 is equal to the square root of pi. And in fact, this is why the square root of pi and factors of pi appear all throughout Hilbert space measurements in quantum mechanics. When we transition to polar coordinates, we obtain the same result as we do with the Cartesian form because integration and rotational invariance commute, and so our base change method holds as a result of a Beck-Chevalley condition. And so we have the following transition that obeys a base change diagram. Our double integral over r squared then transitions into our double integral over the coordinates r and theta, in terms of the circle and the real numbers from 0 to infinity. And the Beck-Chevalley condition is then the guarantor of invariance under that base change that we see here from dx dy to r dr d theta with the different boundaries. And this is why the value pi remains regardless of coordinate representation. And so that means its square root is the universal invariant of normalization under the orthogonal group O2. And so the Beck-Chevalley condition tells us that for a pullback square diagram, projecting first along F and then along G, or projecting first along G prime and then along F prime, are canonically equivalent under the following Beck-Chevalley isomorphism. And this same principle is actually why we can use so many different fields of math to obtain the same result. The same underlying Beck-Chevalley condition manifests in different ways across the following areas of mathematics. We're going to give 5 different examples, but there are many more. In real analysis, it occurs to us through the form of Fubini's theorem and the change of variables formulas that follow. In the field of complex analysis, we see it in the form of contour deformation invariance via Cauchy's theorem. In probability theory, we see it in the form of normalization of the Gaussian measure under orthogonal transformations themselves. In differential geometry, we see it in the form of volume form invariance under diffeomorphisms. And in functional analysis, we see it in the form of invariance of the Gaussian functional measure on Hilbert space. So let's allow the symbol V, which is a symmetric monoidal closed base, and let's allow that symbol to be the category of vector spaces for the real numbers. We're going to select the category of real vector spaces here for our symmetric monoidal base. Let X be a differentiable space such that X is a discrete V-enriched category where objects are points in X. A finite measure mu on the space X can be packaged as a V profunctor where mu of X is a density at X. An integrand F is then a V functor that maps us from the space X to the category of real vector spaces V. and thus the integral of f against the measure u is called a weighted coend. So the integral over x of f through the measure u is equal to the coend in terms of the element x that is inside of the differentiable space capital X of f of x tensored with mu of x as elements of the category of vector spaces V. So that means f of x and mu of x land inside of the category of real vector spaces, the same one. That is very important to keep in mind, because if they don't land in the same category of vector spaces in this case, we don't have a proper coend formula. And so when mu is the Lebesgue measure, this weighted coend recovers the standard definite integral in terms of f of x dx. And so the Gaussian integral in terms of coends can then be written as follows. All we're doing here is replacing that f of x with the function e to the negative x squared. And that, of course, equals square root of pi under this coend. So as it stands, the space x, which is a differentiable space, is the real numbers. And we know the real numbers are differentiable. And so here the density mu of x collapses to the differential dx under this tensor product under the Lebesgue measure itself. When we square this, we obtain a Fubini theorem for coends. So we get the coend in terms of x with our function f of x tensored with mu of x, and that all tensors with the coend in terms of y of f of y tensored with mu of y, and that equals pi. This is also equivalent to the iterated integration given by the coend in terms of x and y of e to the negative x squared plus y squared, which we can call f of x and y, tensored with mu of x tensored with mu of y. So we note that a map phi, which takes us from the two-dimensional Euclidean vector space to the real numbers greater than or equal to 0 cross S1, is a diffeomorphism inducing a pullback push-forward square of profunctors, where phi, acting on x and y, gives us the coordinates r and theta. This allows for a change of base formula that holds due to the Beck-Chevalley condition. And so that coend, that iterated integration that we saw above, is isomorphic to the coend in terms of coordinates r and theta of e to the negative r squared times r tensored with mu of r tensored with mu of theta. So rotational invariance is fixed by the Beck-Chevalley condition under the O2 symmetry group. Now let's consider the Stokes-Cartan theorem in this more general language. So we let the map I, which maps us from the boundary of M back into M, be the boundary inclusion of an oriented, compact, smooth manifold M, and let the cochain complex of omega be a d-Rom complex functor that is a z-graded functor in the category V, which is, in this case, the category of real vector spaces. We are concerned with two fundamental structures here. One, a push forward of chains given to us by the integration over the manifold, which we can represent as a coend that maps us from the space of differential n-forms on the manifold to the real numbers. Two, a pullback of forms, which is given by I star that maps us from the space of differential n-1 forms on the manifold to the space of differential n-1 forms on the boundary of the manifold. And so the exterior derivative that maps us from the space of differential n-1 forms on the manifold to the space of differential n forms on the manifold is the right mate of the boundary operator that maps us from the space of differential n forms on the manifold to the space of differential n-1 forms on the boundary of the manifold under integration pairing. The Stokes-Cartan theorem is then the following Beck-Chevalier identity. That is to say that the coend in terms of x of the exterior derivative of the differential form omega at x, tensored with the volume of M at x, where x is an element of the manifold M, is isomorphic to the coend in terms of y of the pullback of the differential form omega at y, tensored with the volume of the boundary of the manifold at y, where y is an element of the boundary of the manifold. So the Stokes-Cartan theorem is recognized as the canonical Beck-Chevalier identity in the bi-category of smooth manifolds, differential forms, and integration profunctors. This means that the Stokes-Cartan theorem is a one-categorical shadow of a higher Beck-Chevalier identity. In words, the Stokes-Cartan theorem is the face of a Beck-Chevalier cube. The condition that this face, which is a square of the Beck-Chevalier cube, commutes is precisely why the exterior derivative and boundary operator are nilpotent as second order. That's why we get d squared is equal to del squared equals 0. And this is especially true since the square of these operators represent the same morphism expressed in different directions within the cube. And this is the categorical reason for nilpotence and is the true unification behind de Rham theory and geometric topology. And so the Beck-Chevalier cube therefore encodes a three-way compatibility across geometry, homology, and cohomology. So now let's consider homology and cohomology theories in terms of derived ends and coends. So let C be a small category, and let A and B be coefficients, where A maps us from the category C to the category V, and B maps us from the opposite category of C back into the same category V. And the following coend computes a tensor product over the category C. So we get the coend in terms of C of B of C tensored with A of C, and then the following end computes a Hom object of natural transformations. So we get the end in terms of C of the bracket of B and C with A and C. Passing to derived functors gives the familiar homology and cohomology functors respectively. When we pass through the left derived functor on our coend, we get the torsion functor for B and A. When we pass through the right derived functor on our end, we get the extension functor for B and A. And so the classical pairing, which maps us from the cochain complex across the chain complex to the real numbers, is an enriched end-coend evaluation. And so the Beck-Chevalier relation between the exterior derivative, which is a right-derived end-computing differential, and the boundary operator, which is a left-derived coend computing differential, is the following identity. So this bracket in terms of the exterior derivative of omega in C equals the bracket with omega with the boundary of C. And so as a result, the Stokes-Cartan theorem is a shadow of the general statement that derived ends and coends form a paired calculus where the Beck-Chevalier condition ensures base change invariance. So our prior discussion lands us in an extremely generalized theorem in terms of abelian or derived categories as per ordinary ends and coends under the action of derived functors. In the theory of stable infinity 1 categories, for example, Tor and X become the homotopy groups of homotopy coends and ends, respectively, as opposed to just separate functors. In the theory of stable infinity bi-categories, we work with fiber-wise homotopy ends and coends, where the Stokes-Cartan theorem becomes the mate of the statement that the exterior derivative commutes with homotopy push-forward along a fibration up to a boundary term. And so the derived complex with integration along fibers is itself a Beck-Chevalier compatible indexed and stable infinity category, where the entire calculus of derived ends and coends discussed before becomes a fragment of this very fact. In higher infinity n categories, Tor and Ext are higher homological invariants altogether, and so what we have discussed prior is just the zero truncation of this unfolding story. So what is integration really all about? What we inevitably reach is a universal duality between ends and coends as adjoints. And so this coend is the left adjoint of this end. This adjunction is the infinity categorical core of the following principles. Stone duality, which is an equivalence between an algebra of global truth values and a topological space of local states. Gelfand duality, an equivalence between commutative C-star algebras of functions and compact Hausdorff spaces on which those functions are evaluated. Pontryagin duality, an equivalence between locally compact abelian groups and their groups of continuous homomorphisms. Tanaka-Crane reconstruction, an equivalence between a pro-algebraic group and its category of representations. Then we have the Gelfand-Naimark theorem, which is an identification of abstract C-star algebras with concrete norm-closed star subalgebras of bounded operators on a Hilbert space. Then we have categorical logic's semantics and syntax duality, which is an equivalence between a logical theory and a classifying category or topos of its models, where the logical theory is composed of syntax, proofs, and formulas, and its models are semantic realizations of that theory. Topos theory's localic duality, which is an equivalence between locales and complete Heyting algebras, where locales are point-free topological spaces. We have the duality of probability monads and measure spaces, which is an equivalence between describing probabilities via a monad on spaces formed by abstract randomization operators and describing them via sigma algebras in classical measures, where a common sigma algebra is the Borel algebra. Then we have the duality of higher factorization homology and higher co-sheaves, which generalizes the sheaf and co-sheaf duality principle, which itself is already a generalization of the Poincare duality. And this is an equivalence between integrating higher algebraic data over manifolds through factorization homology and viewing that data as higher co-sheaves or co-stacks that assign observables to regions and glue them coherently. Lastly, we can consider a duality in higher physics that is subsumed by the adjunction we have discovered, and that is the ADS-CFT correspondence, which is an equivalence principle between a bulk gravitational theory, an anti-de Sitter space, and a boundary conformal field theory. This is also an example of a holographic principle. The bulk theory is a higher dimensional geometric object, and the boundary theory is a local algebra of observables. And so the ADS push forward is a coend that integrates bulk fields along radial directions, such as through the Witten diagrams formed by the integral over the anti-de Sitter space of the fields at X with the kernel of X and Y. The CFT pullback is an end that performs evaluation and pairing via correlators given by this k-point function, written in terms of the boundary CFT operator at points y sub 1, y sub 2, up to y sub k. The GKPW dictionary, in classical approximation form, also called saddle point form, is given by the following, where S is the stationary action, phi represents classical fields, and O is the boundary CFT operator. The full quantum version of this is given by a Feynman path integral. The classical ADS-CFT correspondence is really a bulk boundary duality where geometry collapses by coends and boundary observables reconstruct by ends. Notice that this is nearly an identical statement to what we have been describing within this video earlier. It's a categorical generalization of the Stokes-Cartan theorem in disguise. We can compute the aforementioned Witten diagrams given by the ADS integral in terms of a coend. So we have the coend for X of the fields at X tensored with the kernel of X and Y. And then the k-point function is given by an end, as follows here, as the end in terms of y of the internal Hom object in terms of the vacuum state 1 and the boundary CFT operator acting on our point values y sub 1 all the way up to y sub k, where in an operator sense we use a tensor product between the boundary CFT terms. We define this as the end in terms of y of the Hom object formed by the vacuum with these boundary CFT term collections. These two ideas are adjoints of each other. Thus, we have expressed a field-theoretic adjunction, which is an enriched Yoneda lemma, that mirrors precisely what we have been describing all along through a generalized Stokes-Cartan theorem as a shadow of the Beck-Shevali condition. In this case, the Hom objects are the internal Hom objects of enriched categories, and our coend is the left adjoint of our end here. So in conclusion, integration is the universal colimit of a profunctor. It is the act of gluing together objects to form another object without losing chosen invariants. In different areas of math, the process of integration shows up in many unique forms that uphold this exact same principle, whether it be through summation, averaging, convolution, push forward of measures, Hilbert traces, or left-Kahn extensions. All of these can be expressed with coends. This means that any universal accumulation of structure indexed by a category is a form of integration. This includes higher coends as well, which involves iterated push-forwards of higher morphisms. In the prior video on naive class theory, integration was a truncation of potentially incoherent global potential into a coherent local object, and it was invariant under all allowed reindexings as per the Beck-Shevali condition. As a result, integration was really viewed as any possible projection or measurement that brings us closer to a coherent idea, even if that projection was none other than enforcing an axiom upon a pre-space or pre-category. Too long didn't read version. Integration is the homotopy coherent push forward of structure along a map. It is a coherent collapse of values, densities, chains, cochains, higher cells, etc. into something that is relatively local, coherent, and invariant under base change. And as coends are the left adjoint of ends, we find that differentiation is a measure of how a global theory changes when local data is perturbed. Thank you for watching.